All right, so I'm going to walk you through this practice CER so you can be better prepared for the real CER and the makeup test. I'm going to post the link to this video at the top here on the final practice version 0. So you'll see this either here or at the very end of the document. So the instructions are: complete the following assessment on your own using a pencil and a calculator, and then hand this in when you're completed. And the scenario is a group of students is completing a project to design and build a bungee cord to drop a 5-kilogram pumpkin from the 5-meter tall roof of the science building. The students are designing the bungee cord so that the pumpkin touches the ground without smashing before it rebounds back upwards. The relaxed length of the cord is 3 meters long. So we know that in this scenario, it always helps to draw a picture. We know that the science building is 5 meters tall. We are going to have a bungee that's 3 meters long. This represents my relaxed length. Okay, and this represents the height of the building again. And now we have Part A. So what K does the group of students need their bungee cord to have in order for the pumpkin to touch the ground without smashing before it rebounds back up? And assume that the height at the bottom is 0. Show both your calculations and describe your procedure for finding the K. Remember, E top equals E bottom. So we know that E1 equals E2. Said that. E at the top, so this being 1 and 2 being the bottom, all you have is GPE. And at the bottom, what you have is 1/2 kx squared. All right, that's EPE, excuse me. And so we know GP is MGH, 1, and EP is 1/2 kx squared. And here it's asking me, what is the K that we need for this situation? The mass of the pumpkin is 5, gravity is 10, and H1 is 5. I need to find K. My stretch for the pumpkin to go all the way to the ground is, so if this is 3 and this is 5, how much does it need to stretch to get to the ground? And that number should be 2 meters. So my stretch is 2 meters, 2 squared. Now I'm going to calculate this. This is 250. Okay. My K, in this case, let me get my calculator. So my K is, let's see here, 250. I'm going to divide by 4. And then divide by 0.5. The K I need is 125 newtons per meter. And so the K I need, I'll write down here, 125 newtons per meter. Describe how your procedure for finding the K. You describe it by just telling me that you utilize conservation of energy to then determine what energies you have at the top versus what energies you have at the bottom, right? And then you just solve for your unknown. You solve for K in this case. Let's go to the back. Now, remember on the front it says we need a K of 125 newtons per meter. That's what we calculated here. We need a K of 125 newtons per meter for this to work. If our K's different from that, then we're not exactly going to get to the ground before we rebound. All right, the students build the 3-meter cord described above. They then collect the data below. They graph the force versus stretch data, and then graph the force versus stretch data, and then determine the measured K value using the graph. So here I have force, here I have stretch. Right? So this is force versus stretch, so my force goes on the y-axis in newtons, and my stretch goes on the x-axis in meters. And let's see, my x goes to 1. If I do this as maybe every, let's see, how many do I have here? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. If I do this as 1 meter, 2, 4, 6, 8, 10, this as 0.5 meters here, 2, 4, 5, this is 0.25. All right, so 1, 2, 3, 4, 5. So I'm just setting up my axes. Perfect. All right, now I'm going to do my y-axis. So I just created a range here that encapsulates all the data here. Now for my y-axis, I'm going up to 88 newtons. So I'm going to make this 100 at the max, 100 newtons. So that means this is 0. I'm assuming this is the same height, but let me check. It's 2, 4, 6, 8, 10. 2, 4, 6, 8, 10. So yes, 20 increments tall. That's 100. This is 50. This is 75. And this is 25. Okay. That makes each unit here 5, 10, 15, 20, 25. So each one of these units is 5 going top to bottom. Okay. At 0, the force measured 0. At 0.25, my force is 21.7, so that's going to be right around here. At 0.5, it's 43.4, so that would mean that at 0.5, I'm a little bit above this 40 mark here. At 75 or 0.75, I am 66.5. So this is 65, so I'm a little bit above this line. And at 1 meter, I'm 88. So at 1 meter over here, I'm 88. This is 75. 80, 85, so I should be a little bit above that at 1 meter. 75, 85, going here, around there. Okay. I'm going to use a ruler to draw a line of best fit. It's my line of best fit. Okay. And now it says here, graph the force versus stretch and then determine the measured K value. So determine the K value you get from this graph, and that is the slope of this graph. The slope of this graph. So if I have 2 points that are on that line, then I can use those 2 points to determine my slope. And if they're on the line. If they're not on the line, then I need to assume some values for points on the line. So I'm going to determine my slope. That's equals y2 minus y1 over x2 minus x1. Okay. If I'm using this point, my y2 is 66.5 because that point is this point. My y1, which is this point, is 21.7. It's this here. It's this value. So 21.7. My x2, so x2 was 0.75, and my x1 is 0.25. Again, my slope is my K value, so I'm really just calculating my K value here. So let's do 66.5 minus 21.7, that's 44.8 divided by 0.5. So I'm going to divide by 0.5, and I get a K value of 89.6 newtons per meter. So my K value is 89.6 newtons per meter. All right. Now this is lower. The K value I get here is lower than the 125, I believe we calculated in the first part. So 125, that's lower. That means that this is a lot stretchier cord. Remember, a low K value means it's really stretchy. High K value means it takes a lot of force to stretch, so it's really not that stretchy intrinsically. Okay, so let's keep that in mind as we move on. Okay, so establish a claim based on the data above. So we're here on part A. Establish a claim based on the data above. Will the pumpkin smash on the ground, or will it bounce back up before it hits the ground? Now keep in mind, we need K of 125 newtons per meter. We measured K of, let's see, what's the measured K? It was 89.6. 89.6 newtons per meter. Now the K we measured, so the students made a band, they measured the K, they got 89.6. That means that's a really stretchy band. If it's too stretchy, then when you drop that pumpkin, it's going to stretch beyond the length that you want it to stretch to before it bounces back up. Okay? So in this case, the pumpkin, because that K value that you measured is lower than what we need, the pumpkin's actually going to stretch a lot more, stretch that band a lot more than we need to. So that means that pumpkin's going to smash onto the ground. All right. So we'll get into that evidence, describing the evidence and the reasoning later. But let's establish a claim. So because our K value is lower, we're going to say that the pumpkin will smash on the ground. This is not a because statement here at all. You're either telling me, do you think it'll bounce back up before it hits the ground, or do you think it's going to smash on the ground? Provide written evidence, okay, to describe, provide written description of the evidence that supports your claim, okay? So the calculated K needed for the pumpkin to bounce back up without smashing is, let's see, what is it? It was, we needed 125 newtons per meter, okay? But the measured K is 89.6 newtons per meter. The measured K is lower than the calculated K. Okay? That's just describing my evidence thus far. I'm not giving any reasoning. I'm not explaining how this influences or how this influences my decision to make this claim. Okay. Now I'm jumping into the reasoning part. Okay. So here I'm going to explain that how the measured K, 89.6, how that being lower than the 125 I needed here leads me to the conclusion that, or the claim that the pumpkin will smash onto the ground. Okay? So the measured K is 89.6 newtons per meter. Okay. Compared to a calculated K of 125 newtons per meter. So I'm going to restate my evidence just in a much shorter way. And now what I want to do is use the language of physics to describe the connection between my evidence and this conclusion. Okay. A lower measured K means that my band or bungee is stretchier or requires less pull force to stretch. Okay, so a lower K means, again, to stretch at a given distance, you need less force. Okay, that means it's a lot stretchier. Okay, therefore, the reduced K means the 5 kilogram mass of the pumpkin will pull the band, pull or stretch the band longer than the desired stretch value. Okay. This would cause the pumpkin to smash onto the ground. All right. I think that's a reasonable explanation. What do you think? Should I add anything else, Miss BS? No, if you weren't listening, that's fine. Okay. I think that's a reasonable explanation. If you're saying that your K value is less, that means your band's really stretchy, so when you put that pumpkin on there, it's just going to pull that band so easily that it's just going to go right to the ground and never bounce back up. Now, if your K was higher, if I got a measured K that was higher than 125, let's say I got a measured K of 150 or 175 or 200, that means that pumpkin's not going to stretch that band as much because your K is higher. It's harder to stretch with a given force. Okay, so when you drop that pumpkin, it's going to bounce back up before it even gets to the ground. Okay, so those are the two possible scenarios you could have. One where the K is lower, that means it's really stretchy and it's going to go beyond what you need it to stretch and smash. Or your K value is higher and it's not even going to get to the ground. It's going to bounce up before it even gets there. So those are the claim evidence reasoning, and then also how you generate the evidence to support your CER. Okay, thank you.